This is a GCSE presentation looking on uses of the motor effect on electric motors. To get started, use your knowledge of the motor effect and Fleming's left-hand rule to work out in which direction the wire would go in each of the four examples below. Pay particular attention to how the battery is orientated. Pause the presentation now, and when you're ready you can restart and go through the answers. Well, if you're to use Fleming's left-hand rule, make sure you line up your first finger with the direction the magnetic field lines, your second finger lines up with the direction of current, and your thumb points in the direction of motion of the wire. And you should find that in number 1, the wire moves down, in 2, the wire moves up, in 3, the wire moves up, and in 4, the wire moves down. And if you notice that when you swap over from positive to negative, and so the current goes in the opposite direction, or we change polarity, that it changes the direction the wire moves in. Also, by swapping the north and south pole over, we also change the direction the wire is moving in. What we're going to look at is interpret diagrams on the motor effect, which you've already just started on, and we're also going to look at how electric motors work. So to start with, before you go any further, it's important to note what we're looking at in the picture is a diagram to show a single loop of wire. It is just one single wire that has been bent into a particular shape. When you go through the diagrams, you'll find that the wire has got different colors and stuff on it. Those colors are only there purely for descriptive purposes to make it easy to see which section we're talking about. This is just standard wire. It can be wrapped in some sort of insulated material, but normally it's just bare exposed wire. So the first question is, looking at the diagram, when we look at the loop, looking at the blue part, what direction will the wire move? Well, if we use Fleming's left-hand rule, the current is moving along the black arrow because it goes from positive to negative on the battery. The magnetic field goes from north to south, so that blue line, the movement should be down. If we look in the pink line, well, in the pink line, again, use your left-hand rule. The current is coming towards us. We've got a magnetic field going from north to south, so it's in the same direction. This time, what we should find is that our motion is going upwards. Remember, always make the shape of your left hand for Fleming's left-hand rule before you try lining things up. Otherwise, your fingers do all sorts of silly things. If you make that shape with everything at right angles, then start lining stuff up, you're much less likely to make a mistake. With one side moving up, the pink side, and the other side moving down the blue side, that actually causes the coil to rotate. However, there is a problem. I'd like you to pause the video for 2 minutes maximum, and I want you to use Fleming's left-hand rule to see if you can identify what the problem is. Pause the video now. Hopefully you might have spotted that as the pink wire moves from the left, it moves upwards and then moves across to the right hand side towards the south pole. It actually moves across the south pole, and Fleming's left-hand rule means that the force exerted on that wire causes the wire to go in reverse. So initially it's going clockwise. Once it crosses over the midway line, it starts to head backwards in an anti-clockwise direction, which in terms of a motor isn't really quite useful. So we have to find a way getting around that. A split ring commutator is the way that we get around that. And if you look at the split ring commutator, what you have is a positive and negative wire connected to the battery. The little black pieces on the end of the wire are actually normally carbon brushes, which rest up against the two metal pieces that are able to rotate. The yellow bits are able to rotate around the grey center pole. And on each of the grey bits we have either side of the loop, and we'll have a look at that in a second. And what essentially happens is, as the two yellow pieces and the wires connected to the loop rotate, they rotate and keep in contact with the carbon brushes. At one instant, the carbon brushes do not touch either of the yellow parts of the commutator. Because the commutator isn't being touched, they technically have no charge in them. However, the momentum of the wires up until that point, the rotation, the force, carries past that point, so it doesn't stop dead. And if it continues on, you'll notice in the far right picture that the wire that originally started on the negative side rotates all the way over to the other side and stays positive. So no matter what happens, the wire of the loop that's on the right is always positive, and the wire on the loop that's always on the left is always negative. What that means is that the split ring commutator ensures that the electricity, the current, is always flowing in the same direction around the loop, regardless of which bit of the loop's on the right or which bit of the loop's on the left. Because the current is always traveling in the same direction, no matter which bit of the loop is on which side, they're always having the same force applied in the same direction. And as a consequence, we have this continual spinning motion. On the left, if we use Fleming's left-hand rule, you'll find that the motion is always upwards. And on the right, you'll find the motion is always down, and you have that constant spinning. Hence, we end up with an electric motor. Just remember, when we're talking about electric motors, we have to have a DC supply. An alternating current would cause the current to flow in one direction and then the other, and as a consequence we'd have the same problem as we had previously without the split ring commutator. So what you have to make sure is that you're either using a battery as your supply source, or you have building some kind of circuit so that the electricity flowing in is AC current turned into DC. Remember, AC comes from the mains, we want to turn into DC. And we can use things like bridge rectifiers, which you do not need to know for GCSE, or we can look at things like transformers and stuff, which we will talk about a little later. Now, there are three main ways we can increase the speed of an electric motor, and you need to know all three. Pause the presentation, try and come up with what you think they might be, and if after 2 minutes you've done your best, move on and you can check your answers. So pause now. Well, the three ways are to increase the strength of the magnet using larger magnets or using different magnetic materials. We can increase the amount of current flowing through the wire, or we can use coil wire to form the loop rather than a single continuous piece of wire. Remember, if we have coil wire, what we're essentially doing is increasing the magnetic field around the wire. The next thing you need to be able to talk about is what can we change that will result in the loop reversing direction. And if you cast your mind back to the very start of the presentation, you may remember how to do this. Pause now, come up with your best answer, and after a minute or so, if you haven't come up with anything, go through the answers and memorize them. If you have, you can always check and hopefully you've got them right. Pause now. Well, the two things we can do are we can change the direction of the current flowing around the loop, also known as changing polarity, or of course we can switch over the magnetic poles so that north and south exchange places. And both of these result in a reverse of direction from clockwise to anti-clockwise. To finish off, create a flow chart that describes and explains, so it's what happens and why it happens in an electric motor. So a flow chart to describe and explain what happens in an electric motor.